The heavens above our Earth have gripped the imagination of generations of human beings.
Gazing into space and the dream of discovering the origins of humanity is as old as civilization itself.
The search for answers. Where do we come from? Where are we going? What is out there in this endlessness?
You notice a sense of the present out there simply because space is so close.
Since the early times, scholars and scientists created instruments to allow them to look into space from the Earth.
In search of humankind's position within the universe and the origin of our own home, planet Earth.
We can look so far back, almost to the beginnings of the universe.
Because looking into space is also looking into the past.
But it's not only from space that we can explore the universe. The Stratospheric Observatory for Infrared Astronomy, or SOFIA, is an observatory inside an aircraft.
The future of SOFIA in terms of what the results could be are only limited by one's imagination.
Like any aircraft, the airborne telescope has to undergo regular maintenance. The jumbo jet is due for a D-check, a complete overhaul, so SOFIA is being flown to the Lufthansa maintenance base in Hamburg.
SOFIA is primarily an aircraft, a large aircraft that flies at a very high altitude and is deployed there as an astronomical observatory for infrared astronomy.
Developed in close collaboration between the German Aerospace Center DLR and the American Space Agency NASA.
For scientists, it's a tool for gaining new knowledge about the universe and in particular the processes involved in the formation of stars and planets, right up to the question, did life originate on planets or did it come to us from outer space?
Scientists use SOFIA to observe the stars and planets in the infrared region. Water vapor in the atmosphere prevents such observations from the ground, but the jumbo carries the telescope above this disruptive layer.
Our goal and our mission is to conduct infrared astronomy, to investigate and answer some fundamental questions about the origin of our universe and the processes involved.
Overhauling a plane like this is also a rarity, even for the specialists at the Lufthansa base. New territory for the Hamburg engineers.
Working for NASA is certainly very special for us, and so is a plane like this. We've never had anything to do with such an aircraft before. We've had no previous contact with this plane whatsoever. A 17-ton telescope is certainly extraordinary, and the equipment too is not what we're used to.
Normally, the private jets of heads of government and the super-rich are converted and maintained here. So the Hamburg engineers are very familiar with extravagant aircraft.
A general overhaul is normally carried out after 6 years, and here it takes us 2 or 3 months to complete. It's much quicker for commercial aircraft, but for a plane like this, it'll take a bit longer because of all the special installations.
All relevant parts will be overhauled, with particular attention being paid to the engines.
These two engines are primarily fitted with parts that have a designated maximum service life, which they've now reached and so have to be replaced. That's the reason why we're now removing both engines and fitting the plane with 2 new ones.
The airplane was built in 1977 and began its career as a passenger jet. At the end of the 1990s, it was taken out of service and bought by NASA.
There are plenty of wearing parts. The fuel pumps, the hydraulic pumps, the starter, the ignition if you like. This one here is a compressor starter unit. They can all provide reasons for being replaced. There are air pipes here as well that can break or crack under the thermal load.
Jet engines were developed in the mid-1960s. real dinosaurs compared to modern turbines.
Generally, these classic high bypass fan engines still have manual control. With current technology, it's all ones and zeros. Everything's controlled electronically, and there's no external intervention possible. Everything's preset at the factory and then just installed.
The jumbo jet's landing gear has also been overhauled and is now ready to be reinstalled.
Here we have two of SOFIA's undercarriages. What we see here are the so-called wing gears, which are installed underneath the wings and carry the main load of the aircraft. Here you can see that everything's new. These undercarriages have been completely overhauled and are now being treated just like new ones.
SOFIA is a Boeing 747 SP, a version of the famous jumbo jet, but 14 meters shorter. SP stands for Special Performance. The 747 SP is smaller and lighter than a normal jumbo, but has the same engine performance.
This enables the aircraft to fly extremely high, ideal for an infrared telescope. The former commercial airliner was disassembled and completely rebuilt in Waco, Texas. A pressure-resistant chamber was built into the rear section of the fuselage to house the infrared telescope.
The telescope's primary mirror is made of ceramic glass, similar to a ceramic stovetop, and measures 2.7 meters in diameter. Like the entire telescope, it was developed and built in Germany for the German Aerospace Center, the DLR.
The DLR also took on the task of transporting the 17-ton telescope construction across the Atlantic. In September 2002, 5 years after building began, the highly sensitive telescope was loaded onto a Beluga cargo aircraft and flown across the Atlantic to Waco, Texas, for installation.
This extraordinary cargo plane is normally used for transporting aircraft fuselages.
Once in Texas, German and American engineers set about installing the telescope in the modified jumbo. A task of immense precision that took several months to complete. In July 2003, the primary mirror was finally installed.
Even though SOFIA itself could not actually take off at the time, the telescope was now operational.
The idea of actually putting a telescope onto a plane isn't that old, only around 50 or 60 years. The first astronomer who was famous for this was Gerard Kuiper. He wanted to put a telescope on an aircraft and fly it into the upper atmosphere. So he got himself a small business jet and installed a telescope with a diameter of about this size, 30 centimeters, and with this he could fly around at high altitude for about half an hour. He made some fantastic discoveries, and so NASA said, well, if it's that promising and there's so much to discover, we'll build a bigger one, a bigger plane with a bigger telescope, and that was the famous Kuiper Airborne Observatory.
At the beginning of the 1970s, based on Gerard Kuiper's idea, NASA purchased a military jet, a 4-engine Lockheed Starlifter troop transporter that could operate at high altitude.
They cut a hole in the fuselage behind the cockpit, installed a mirror telescope with a diameter of 91.5 centimeters, and named the whole thing the Kuiper Airborne Observatory.
With this flying observatory, scientists observed astronomical objects, especially in the infrared region, until 1995. The scientists discovered the rings of Uranus and the thin methane atmosphere around Pluto.
The Kuiper Airborne Observatory operated in the skies for 2 decades, and its success proved the importance of airborne astronomy.
It flew successfully for 20 years and helped us gain so many new insights, like the discovery of the rings around Uranus.
It was purely a NASA project, but German scientists were invited to take part because of the scientific instruments they had. And then there was the idea of building something bigger at some point to do even better science.
And with that, SOFIA was born. Once the telescope was in place, the rest of the scientific equipment had been installed, and the aircraft completed, SOFIA was ready for its first tests on the ground.
Though the mirror still hadn't been given its final coating, SOFIA was already capable of undertaking its first observations of the stellar skies. In these tests, the function of the telescope and all the related systems were checked thoroughly.
The mirror was then taken out again and given a coating of pure aluminum at the NASA Ames Research Center in California. It's this vapor deposition of aluminum that transforms the piece of glass into a highly reflective optical instrument. Only a flawless and perfectly clean mirror can deliver sharp and precise images of distant celestial bodies.
For the vapor deposition process, the glass mirror was hung in a vacuum chamber. Only 2 grams of aluminium were needed for the coating. An ultra-thin, flawless surface coating was the result.
The researchers were now looking at the perfect mirror.
Then, in December 2009, SOFIA took off for one of its most exciting tests. For the first time, the telescope door was to be opened completely in flight.
At about 500 kilometers per hour, the pilot pushes a button to open the giant roll-up door. Despite all the simulations in the wind tunnel and on a computer, this was a moment of extreme tension.
The Airborne Observatory completed an extensive series of test flights over California's Mojave Desert, the ideal opportunity for engineers to examine the movements of air in and around the telescope. At the same time, flight characteristics, in particular aerodynamics, and the structural stability of the modified jumbo were also tested. By the end of 2010, SOFIA was able to begin the actual scientific testing.
The full-scale overhaul in Hamburg involves the jet being almost totally dismantled. Over 50,000 working hours are scheduled for this inspection.
So here we are standing under the wing where it joins the fuselage. Here you can see parts of the air conditioning. These are the so-called manholes where you can get in and carry out the relevant checks and maintenance work. Our main task is to carry out structural checks here in the tanks and check the fuel supply lines. Cables have to be inspected as well to see if they're a tight fit or if they're brittle. We also have to be sure the tank doesn't leak, so we check it and then replace it if it's necessary.
The Hamburg technicians search meticulously for even the slightest damage. Everything they find is recorded and then repaired.
And here we have a classic example. A defect was discovered here, and you can see that the cover is broken. Here there are access bolts that can be unscrewed, and then this seam, this paneling here, can be replaced. It's a seal that makes sure the air can continue to flow underneath the wing uninterrupted. It'll be replaced, painted and screwed back on again. And then it can be ticked off as finished.
Every screw, every aluminium panel in this aircraft is inspected and checked. After all, The jet itself is over 30 years old.
But with the proper maintenance, that's no age for a plane. The basic design for the 747 dates back to the 1960s, and that means it works mechanically rather than electronically.
So in this area here is the rear spar, the wing, and the center tank. You can also see the hydraulic supply lines here, and the steering cables for the so-called flight controls. In other words, the steering elements that get the plane to fly to the left or the right. On this plane, the steering is purely manual and mechanical. You have to remember, the aircraft was developed in the 1960s, in the last century, and the technology we can see installed here is now well over 50 years old.
SOFIA's home base is the NASA Research Center in Palmdale, California. This is where the Airborne Observatory takes off on its missions.
The most impressive feature is this large opening, which can be closed all the way down to here by this door. Then there's also this device known as an aperture with this ramp here. When the plane is flying through the atmosphere at 850 kilometers an hour, the air flows over this device and elegantly down the side again here. This ramp stops the air from flowing into the cavity and hitting the telescope, as this would throw it off its target and you wouldn't be able to keep it stable.
Thanks to the sophisticated aerodynamics, the wind speed in the telescope cavity is only about 80 kilometers per hour when the doors open.
This dark structure here is a very rigid carbon fiber structure with the same stiffness as steel but much lighter. One of the main aims was to make this telescope as compact as possible, because a 747 is big but not infinitely big. That's why the telescope had to be both compact and very light at the same time.
SOFIA's base is located on the Edwards Air Force Base. This is where Chuck Yeager took off on the first supersonic flight in history.
SOFIA's missions begin in the early evening. By the time the instruments are all checked and cooled down, and the plane refueled, night begins to fall. SOFIA's first purely scientific flight took place in late 2010.
The airborne telescope takes off into the night. After some 45 minutes, the aircraft will reach its operational altitude of around 12,000 meters. More than 10 hours of flying and astronomical observations now lie ahead of the crew and the scientists. SOFIA is a large flying laboratory, a jumbo jet packed full of state-of-the-art scientific equipment, and with a giant telescope at the rear.
Once they reach operational altitude, the pilots open the telescope door. The SOFIA locks onto its target and doesn't lose it again.
A target that's hundreds of thousands or even millions of light years away. The images reflect the past of these stars.
The atmosphere inside SOFIA is one of scientific practicality. These passengers bring their food and drinks with them. There's no place for flight attendants on this jumbo. The crew is divided into technicians and scientists. The technicians are responsible for the control and functioning of all the instruments, but most especially for the stable alignment of the telescope. This stands perfectly still, locked onto its target. What moves is the aircraft around it. The aligned mirror doesn't move a single fraction of a millimeter. Otherwise, it would lose its target immediately.
SOFIA's observations take place exclusively in the infrared region. This light is invisible to the naked eye, but perfectly suited for the exploration of the universe.
If you want to investigate planets or interstellar clouds, or if you want to investigate the formation of stars or planets, you have to go into the infrared region because in the visible spectrum there's nothing to see. Infrared is heat radiation. Everything between 1,000 degrees Celsius and minus 270 degrees is warm. We can't see this radiation, but we have instruments that can see it and cameras that work in infrared. Space looks completely different when observation is done in infrared, and you look at the results. You don't see stars anymore. You see luminous clouds, luminous gases, clusters, and cool objects.
Astrophysicists are on a never-ending journey of research and exploration to the very limits of our universe and beyond. The Earth is no more than a grain of sand on a gigantic beach, and our solar system just one among myriads of others, a satellite in infinity. It's also a journey to the limits of our knowledge, in search of the blueprint of the whole universe. A journey that is increasingly bringing new insights in ever shorter intervals.
An expedition that also pursues very concrete research goals, like the search for planets outside our solar system, exoplanets.
Even amateur astronomers can observe exoplanets today because many exoplanets orbit in such a way that they pass in front of their star's surface. And when they do, the star's light intensity is reduced and the star appears slightly darker. Only by fractions of a percent, but modern camera systems can detect this. And then if it recurs every few days, you know, aha, this is a regular event. There must be a planet in orbit.
It's the search for a second Earth. The search for distant planets orbiting stars beyond our solar system, which may provide conditions for life to develop.
The questions regarding exoplanets are very old, and one of those questions is, are we alone?
So, astronomers and astrophysicists are not only concerned with the mechanics of the universe. There's always a philosophical aspect to the search for beginnings and gazing far back into one's own past.
Where are human beings in the great scheme of things? I think this question shows humanity's need to describe its world and make it comprehensible. Aristotle propagated a geocentric view of the world, with the Earth as the center, surrounded by the various spheres with the planets, and in the outermost sphere were the fixed stars.
The Greek philosopher Ptolemy also saw the Earth as the center of the universe. It took almost 1,500 years before this idea was challenged. Nicolaus Copernicus completely changed the focus. In his world, the planets and consequently the Earth as well moved around the Sun. His research was based purely on calculations, but it was only through a groundbreaking invention that his theories were reinforced.
There were lens makers in the Netherlands who'd been trying to make spectacles and then also had the idea of combining two of these lenses to make a telescope.
Galileo's observations supported the new worldview of Copernicus. This invention gave him the ideal instrument for substantiating up his theories.
Galileo Galilei heard relatively quickly that telescopes had been invented in the Netherlands. The reason why Galileo became so famous with the telescope is simply because he was the first to use one for astronomical observations.
This was the birth of modern astronomy. New worlds opened up before Galileo's eyes. The telescope had opened the door to the universe. All over the world, people began to build increasingly larger and better telescopes. The end of the 19th century was the heyday of the large-scale refractors, gigantic refracting telescopes housed in veritable cathedrals of astronomy.
In 1899, the Great Refractor was completed on Telegraph Hill in Potsdam.
The Great Refractor was intended to be a showcase instrument to show that the scientific research being done here in Prussia was among the most advanced forms of science in the world.
And so the Kaiser himself came to the inauguration of what was then the world's largest telescope. A great believer in progress, the regent saw science as a means of enhancing Germany's prestige in the world. The next generation of stargazers would spend their nights here, observing the firmament, always in search of new knowledge and discoveries.
The Great Refractor in Potsdam is one of the 4 largest refracting telescopes in the world. Up to 1968, it was still being used to explore the universe.
Right next door, 2 decades and a world war after the Kaiser's visit, an observatory was created based on a completely different principle. The tower, built by Mendelssohn in 1919, houses a solar telescope.
Like the Great Refractor, the tower belongs to the Leibniz Institute for Astrophysics in Potsdam. The observatory was designed by astrophysicist Erwin Finlay-Freundlich to validate or disprove the theory of relativity published by Albert Einstein only a few years earlier. And that's why the structure carries his name, Einstein Tower.
Astrophysics is determined to a great extent by the observation of the Sun. It forms the basis for understanding the structure of stars. The Sun Observatory in the almost 100-year-old Einstein Tower is still fully functional.
What we now have to do is align the dome so that the sunlight can fall directly onto the mirror.
The mirror beneath the dome directs the sunlight into the actual telescope in the tower.
This mirror catches the sunlight, and you can see here it has an axis parallel to the rotational axis of the Earth. This means when the sun moves across the canopy in this direction, we follow it with this mirror. And then this mirror then sends the light to the second mirror, which only has the task of sending the light down here to the tower telescope, where the light then passes through a 60-centimeter lens. This lens has a focal length of 14 meters and creates a sun image 14 meters in diameter in the optics laboratory, the Einstein Tower's basement laboratory.
The telescope stands vibration-free on its own foundations, surrounded by the tower as its protective shell. The redirected sunlight falls downwards through the tower telescope towards the cellar.
Then the sunlight can enter the basement laboratory.
Even today, the Sun Observatory on Potsdam's Telegraph Hill is still a powerful scientific facility. The actual research lab is located in the tower basement. Once it has arrived here, the sunlight is redirected yet again.
The light hits this mirror here and is directed across this optical bench where we can test instruments. Then it falls onto this wall, and this is where the spectrograph slit is located.
The spectrograph is the heart of the observatory. Here, the sunlight is broken down into its individual wavelengths, and each wavelength corresponds to a single color. Physicist Joseph Fraunhofer noticed that there are striking lines in the sun's color spectrum. He was able to assign individual chemical elements to these spectral lines, which means that they can be used to determine the chemical composition of the sun.
The observatory was originally built to verify Albert Einstein's general theory of relativity. Although this undertaking failed, Einstein was appointed lifetime chairman of the observatory's board of trustees.
People met here to discuss the results of their work. There were various meetings here, and the board of trustees also met here, so Mr. Einstein would have also been present. Here are lists of times for which cameras were used for observations and when. In principle, these are the Einstein Tower's laboratory records, and they enable us to evaluate the data collected here, and they still do so today. These are photographic plates with which, weather permitting, photographs were taken of the sun's entire surface every day. Here we can see the sunspots lined up along the equator. Here, smaller groups extending from the edge of the sun right into the middle.
Even today, the tower telescope still plays an important role, because this is where young scientists are trained and where new optical instruments are tested.
The sun is the source of all life on Earth. Its light and warmth profoundly influenced the existence of humankind. Many generations idolized it or feared it. When it darkened, it meant plague, death, and the end of the world. The sun determines the times of day and controls the climate on Earth. An enormous nuclear reactor of seemingly infinite energy. A star whose presence we can actually feel. And yet, it's just one star among billions in our galaxy.
Europe's largest and most modern solar telescope stands on top of a volcano on the island of Tenerife and is named Gregor. The clear, calm air above the clouds offers ideal conditions for solar observation. Einstein Tower scientists from the Leibniz Institute for Astrophysics in Potsdam participated in Gregor's development. The telescope provides images of the Sun in as yet unprecedented quality.
It's important for solar telescopes to have a large mirror, in this case 1.5 meters, in order to collect a great deal of light. This is because our instruments have to make extremely precise measurements, and for this you need a lot of light. The larger the mirror, the smaller the details we can see on the Sun's surface.
Astrophysicists in search of the secrets of our universe.
Good morning, Discovery. You got a go for HST deploy ops.
In April 1990, the Space Shuttle Discovery is launched from the US spaceport in Florida. In its cargo hold is the Hubble Space Telescope.
The eye in space is named after the American astronomer Edwin Powell Hubble. It was he who discovered the nature of spiral nebulae, and a formula he devised made it possible to estimate the age of the universe.
Only the advent of space travel enabled stars and planets to be observed far above the disruptive layer of the Earth's atmosphere.
Space travel fulfilled an age-old dream of humankind, the exploration of the universe from outer space. The unobstructed view into infinity.
And so, putting a telescope into space was an obvious step. Unobstructed observation, free from environmental influences and the blurring mantle of air around the Earth.
You know, the influence of the atmosphere is astonishing. Look here. These are two pictures of Mars, taken through two similar telescopes. One is taken from Earth through the atmosphere, and the other one was taken here. Quite a difference, isn't there?
The Hubble telescope was to be humankind's eye in space.
But the eye proved to be short-sighted. Hubble sent back blurred images. That was a shock for the scientists.
The Hubble telescope consists of a number of individual components, and they didn't work well together because of a flaw in the primary mirror's curvature. And that basically means Hubble had glasses with the wrong lenses, so it couldn't see clearly. But you can't just bring the primary mirror back to Earth and correct it. You need a second lens to correct the fault in the first one.
What then happened was probably the most expensive eye operation the world had ever seen. Astronauts flew several missions to carry out repairs on the space telescope, and it worked. The fault could be corrected in space.
The science community was appeased. Hubble provided the expected images in crystalline clarity.
Images of a bizarre, fascinating, and yet bewildering beauty. Landscapes of light, stellar dust, and gas clouds formed by cosmic winds and radiation. Never before had human beings been able to gaze so deeply into outer space. Hubble can look far back in time. The telescope picks up light waves that left their source over 13 billion years ago.
At the moment, we're in the golden age of astronomy. The results delivered by satellites orbiting in space, like the Hubble Space Telescope, are just fantastic. The increase in our knowledge about space missions to other planets is incredible. Textbooks from the last 50 years can all be thrown away because our knowledge is now increasing so quickly that we find something new every few years.
SOFIA only flies at night. The observatory needs the dark, starry sky for its observations. Meticulous planning goes into every mission.
The art of flight planning lies in combining the individual flight segments in such a way that all the desired targets can be observed during the flight. We fly a zigzag pattern all night long, either over the US or the Pacific. For air traffic control, that's quite unusual, because we don't fly from A to B with a definite destination, but follow the movements of the stars. This led to lengthy discussions in the initial phases until air traffic controllers understood what SOFIA was doing all night.
A telescope housed in an aircraft combines the benefits of terrestrial observatories with those of observatories in space. 90% of the disruptive water vapor layer lies below SOFIA. And just like with telescopes on the ground, the researchers can mount various additional devices or cameras at any time.
You could put such an observation post into space, of course, but first of all, it's very expensive, and then most of the time when you're in space, you've no longer any control over the satellite. Meaning, when the satellite's up there and it works, that's fine. If it doesn't, hard luck, and that's the end of the mission.
SOFIA also offers another advantage. Infrared telescopes have to be cooled considerably. Otherwise, their own heat radiation would influence and thus falsify the observations. The coolant used is usually liquid helium, and telescopes stationed in space can only take a limited supply with them.
At some point, the Herschel satellite ran out of coolant, and although everything else worked perfectly, the mission was over. As an aircraft, SOFIA can land, refuel, and take off again. That means we're fully supplied again.
NASA test pilots are responsible for flying SOFIA. They follow the flight plans drawn up by the scientists.
SOFIA's observation flights last between 10 and 11 hours. That's just the pure flying time from takeoff to landing. Then there's between 8 and 8.5 hours observation time, during which the scientists can actually carry out observations of stars. If we fly west, we can observe targets in the southern sky, and when we fly east, we can observe objects in the northern sky.
Besides the crew of 3, there are up to 20 scientists and technicians on board. On each mission, the telescope targets different objects.
Normally, ground-based telescopes are built on solid rock with lots of concrete and steel in their foundations to prevent them from wobbling. And here, a large telescope has been built on a flying platform that's constantly in motion. When you fly on SOFIA, you can see the telescope working and moving in the rear fuselage all the time, but in reality, the telescope is standing still looking straight at the stars while the aircraft moves around it.
SOFIA's observation flights last the whole night. Tiring but very fulfilling research work.
The feeling you get when everything works, the plane flies, the telescope works, the instruments do the measuring, and you get the data, and gradually see an image emerging on the screen, a mosaic being put together. And then you see the results. That's just fantastic.
However, when one sees SOFIA in the Hamburg maintenance base, it's hard to believe that this observatory will ever fly again. The technicians dig right down into the bowels of the aircraft. Kilometers of cables have to be checked, each one individually. Fittings, interior paneling, the ceiling, and even the floor have all been removed.
The entire floor is unscrewed and removed to carry out the required structural inspection here. So let's go back towards the rear a little.
Where technicians and scientists are normally at work, only an aircraft skeleton remains. Only the telescope itself is being maintained by NASA.
Here you can see a switching cabinet for controlling the telescope, and this is where the telescope goes. Down here is where the instrument is normally flange mounted. It can be replaced, and that's the special thing about SOFIA. You can see the bearing here, the new pressure bulkhead we had to install, and the enormous amount of work we've had to put into the conversion. And you can see over here in this part of the cabin, there are the control panels, the controls and the monitoring tables. There are 3 of them altogether. There's a small conference table on the other side, but otherwise the cabin is very sparsely furnished.
The overhaul has brought a number of defects to light. Lufthansa technicians are now removing rivets so they can dismantle parts of the aircraft's load-bearing structure.
This here is the cockpit, and we're now in the process of replacing an entire frame piece. During the inspection, we noticed a crack had formed in this frame, so we're replacing it. That's quite a complex operation, and our estimate is that it'll take about 10 days to remove it and do the preparation work for installation, and then another 10 days to actually install the new one, working in 3 shifts, 7 days a week.
SOFIA's cockpit is also being completely renovated. Besides modern electronics, the pilots are getting new windscreens.
Air bubbles have formed between the windscreen's intermediate layers, so the screens have to be replaced. And we've also changed from acrylic to glass windscreens. That's a modification that we'll be carrying out here at the same time.
At the moment, the plane is being willfully dismantled, and I only hope Lufthansa can put it back together again. Of course, I'm in no doubt they can, so I'm quite relaxed about it.
The AIRBORNE telescope will be spending a good 6 months firmly on the ground. That's how long it will take the Hamburg technicians to get the aircraft in a condition that's as good as new.
By the end of this downtime, we'll have the plane airworthy again, and we'll be able to carry out the relevant ground tests before we get to the actual flight test stage. We'll check all the systems, and only then can we safely return the aircraft to the operators.
This is a new tool. This is a new observatory, and with the completion of this heavy maintenance visit, we will be in a position to launch full speed ahead into our operational mission.
When it leaves the hangar in Hamburg, SOFIA will fly back to its base in Palmdale, California, completely overhauled and modernized. The next missions are already planned. The AIRBORNE telescope is scheduled to complete over 100 flights a year. It will investigate newly born stars, gas nebulae, and planets beyond our solar system. And as always, the explorers are only at the beginning.